Hello, good morning everyone. It's a pleasure to be here again to introduce our friend Alessia Mandini. We will resume the mini course about everything you want to know about polygons, but we are afraid to ask. Thank you, Alessia.
Is it close enough? Good. Okay. So is there something you want to know about polygons, some curiosity that came after last lecture? If not, let me... Yeah, yes, of course. Yeah. So let me do a little resume that will also be helpful for the follow-up. So one way I described polygons was via quiver varieties, and in particular, I used this special choice of a quiver that was the so-called star-shaped, where I have n outer vertices and a central vertex that I call 0, and arrows all pointing inside. I also said that my dimensional vector is 2 1 1s, which means that I make choices C2 and C for the vertices of the quiver. And in this setup, as I explained last time, the representation of the quiver is, I will recall the homomorphism from C to C2, because in this way I can recall that my coordinates are QI maps from C to C2. And also let me recall that the group acting in here is U2 times the torus of diagonal matrices in UN, quotiented out by the diagonal circle in that product. And in this setup, the polygon spaces M alpha can be described as the symplectic reduction of the representation of this quiver that, as you can see clearly, C to N by the group K at the level set. For the moment map, we choose 0 alpha. Remember last time I had the moment map conditions on the board, and there were all details. Okay. Okay, very good. So in particular, last time I talked about the wall crossing, so how the polygon space changes when alpha crosses a wall in the set of admissible values. There is another feature that I want to mention because I like it. I think it's really nice. That is the so-called bending action. Maybe it's not particularly relevant for the results I chose to present, even though I used it for computing the cobordism, etc. But maybe it's a little bit of an off-topic, but it will be about 10 minutes. And I think it really helps a lot to understand the geometry of these polygon spaces. So it goes as follows. We have a polygon, whatever, and assume. So let's call D K the kth diagonal from the first vertex. So I unfortunately called my edges V1 through Vn last time, so I will 1, 2, 3, 4, 5. So I will stick to my notation, and the first diagonal, for example, will be this one. This will be my D1. This will be my D2, right? So what we have, dk, is just the sum of the vectors V1 all the way to K plus 1, probably. If I'm not, maybe I can take my notes to keep the notation. And then what you can do is you can bend the edges before the diagonal. So in the drawing, the first and the second edge, you can bend these two along the diagonal and let the other edges of the polygon fixed. Okay? If the diagonal has non-zero length, you can normalize, if the diagonal has non-zero length, this is a well-defined thing to do because you have an axis of rotation. And then you can normalize the rotation so that you define an S1 action, which is rotations around this diagonal. And if we do it for the second, we are bending the first, the second, and the third edge along the second diagonal, and so on. Okay? Sorry, let me go to the correct page. So what we can do is the following.
Sorry, how much does depend from the fact that V1 is the first vector?
Yes, so this is a choice I made. The definition that you find in the literature is for every diagonal. Of course, you can do it. But my aim, that I will do it in a moment, is to define a toric action, or as good as it gets to close to be a toric action, on the space. So to do that, I need to choose a system of n-3 diagonal that don't intersect in the interior of the polygons, because if they intersect, I mix up the... So for example, if you have an hexagon, 1, 2, 3, 4, 5, 6, the other classical way to do it is choosing the caterpillar. It's so-called caterpillar set of diagonals bending along those. But if you fix a vertex and you consider diagonals going out from that vertex, you are guaranteed that they won't intersect in the interior of the polygon. So.
Find the others as a combination of the one you fixed, or you're missing something in this way?
I didn't understand.
The one the diagonals that you are not considering,
Yes.
the bending along these diagonals, is recovered as a composition of other vectors, or?
No, I mean, you can, for example, for the hexagon, you can, if alpha is such that, and now I will write, you can define two toric actions. One is bending along the, there are different toric actions. Okay. So this was the idea, and then what you can do is essentially, so let me, yeah, okay. I will write what I said now in Word. If dk at the polygon P is different from 0, then you can define the flow of hk v1 vn, which is exactly what I said. So it takes dk p vector product v1. I have problems, sorry, with this. I keep erasing them. Excuse me for the records. And dkp, the last one that I banned, if I didn't do the computation wrong, should be k plus 1, and then the others I let free. Okay? So this, the Hamiltonian function of this flow is the length of the diagonal. Consider this with Hamiltonian function Lk, which is equal to the norm of the kth diagonal at the point P. Okay, Lkp is the norm. So here, choosing, so hence, if alpha is such that dkp is different from 0 for every k that you can possibly define, so I think we are going up from 1 to n minus 3, and for every p in M alpha, then this defines, then by normalizing, this defines a t n minus 3 action, a toric action, on the polygon spaces M alpha with the action angle coordinate given by the length of, let's say, Li and theta I, where Li is defined above. It's for each polygon the length of the ith diagonal. And theta I is the angle of rotation around the ith diagonal. Okay. One thing I wanted to do before making a few comments is that I think this gets a really neat picture for the case n equal to 5, where the torus is two-dimensional, and thence the moment map is in R2, so everything can be drawn easily, right? So it's, in a way, the drawing I've done before, but let me redo it here. 1, 2, 5, so V1, V2, V3, V4, and V5. And so this is the first diagonal, D1. This is the second diagonal, D2. And then you have that under the assumption that you have chosen an alpha such that the diagonals don't vanish, you have a moment map from the space of polygons, M alpha, to R2, that takes a polygon P to the length, to the pair length of the first diagonal, length of the second diagonal. But what does it mean? In R2, we can draw it exactly, because what we are, what are the conditions? This can be read geometrically out of the drawing, because what we require is that these three triangles exist, right? We are bending along the first diagonal. This triangle, V1, V2, D1 should exist. We are bending along the third diagonal. D1, V3, D2 should exist, and also the last one, D2, V4, V5. So what we get are, in fact, triangle inequalities, if you work it out. So in here, you will have, what are the options for the length of the first diagonal? Well, it is either the difference of the lengths of the first two vectors or their sum. So it's alpha 1 minus alpha 2 in absolute values, or alpha 1 plus alpha 2. These are the minimum and the maximum possibility for the first diagonal. Then for the diagonal D2, what are the possibilities? They are at least, well, it can be, V4 minus V5 in absolute values. Sorry, alpha 4 minus alpha 5, or alpha 4 plus alpha 5. So this defines kind of a square like this. But of course, not all such possibilities will be in general achieved, because it may be that we don't have space enough to go up one the other. So if you work out the triangle inequalities, it comes out, it's really just the triangle inequalities written up, that this amount to cutting out this rectangle with these three lines that are, of course, L2 equal L1 minus alpha 3, and the others are the obvious one. This is L1, what is this? L2 equal to minus L1 plus alpha 3, maybe I didn't write them down. Let's not make a fool of myself. So the moment polytope in the end will be the intersection of this rectangle with this unbounded region. In this case that I drew, it's like this one. So it's very easy to compute. You can actually draw a map of all possible moment polytope that you can obtain. And in this case, you also classify, so in this way, you can figure out that the polygon spaces for n equal 5 are either the CP2 or P1 times P1, or CP2 blown up at most 3 points. These are the possibilities that you have for the several chambers of admissible values. Okay, so if you did the homeworks that I left on Monday, you should know what is the different type of the equilateral polygons with 5 edges by wall crossing. But if you didn't, you can easily read it out from here. I will also not do the details for this, but just as it is an interesting case, I will dedicate a minute to it. So this is one case where you cannot find a system of non-zero diagonals, because whatever you do, you will have, the first diagonal can be 0 and so can the second. But you can easily twiggle it around a bit. You can do a 1 plus epsilon, 1 plus epsilon. This will have the first and the second diagonal that will be non-vanishing, and you're still within the same chamber because you did a little move. So this implies that the two manifolds have the same diffeotype. And then if you compute it, you see that this will give you a shape like this, the moment polytope. Right? Which is the most that you can get. It's CP2 blown up at 1, 2, 3 points, right? I do this symbol for, let me write it in words, blown up at 3 points. Okay, comments or remarks? The first one is the one I was already saying, answering to Michele's question. So any system of n minus 3 non-vanishing and non-intersecting, meaning non-intersecting in the interior. Diagonals determine a toric T n minus 3 action on M alpha by bending. Okay? It's not necessary to choose the one going out from one specific vertex, but also because we have seen on Monday that reordering the edges doesn't change, M alpha is symplectomorphic to sigma alpha for any permutation of the edges. You can always, well, I'm not sure if you can always rearrange things, but anyway, you can do it for any system of n minus 3 non-vanishing and non-intersecting diagonals, so it's a bit more general than this. And also, this always defines a toric action on the open subset where the diagonals don't vanish. Okay? So there are a few things that you can do. So this bending action can be helpful really in a number of situations. You can twiggle a bit, staying within the same chamber of admissible values of alpha. You can also just consider the open set where the diagonals don't vanish. So polygon spaces are not always toric, but they have still a rich structure about that. Okay. If you want to know more about bending action, you can also ask Dimitri, who is sitting in the audience, and he has nice insight on the subject. So, otherwise, let's move to, I had in plan to talk of relations of polygon spaces to other, with other, to or with relations to other moduli spaces. And also for time reasons, I will be very brief. I will mention the two classical that are the relation with the space of representation of a punctured sphere and the relation to the moduli space of parabolic bundles, on which I will spend more time. I mean, it will be, in fact, the rest of the lectures. So the relation with the representation, so let's consider the fundamental group of, the representations of the fundamental group of the punctured sphere, punctured in exactly as many points as our edges, and representation in SU2. Okay? The claim is that this is diffeomorphic to M alpha, and I'm not sure if this is a symplectomorphism. I have been wondering for a bit of time. I've been searching in the literature. I haven't found, but this doesn't mean that there isn't. It just means that I... but it would be interesting to know. And how does the correspondence goes? Well, it is pretty explicit, because this space of representations you can think of as n matrices that I will call G1, Gn, right, in SU2n, with the following two conditions. You want G1 times Gn to be the identity, and you want to prescribe the holonomy around the punctures, right? So you will, this is done, for example, by saying that the trace of Gi should be twice cosine of pi alpha I. And then how does the correspondence, how can you construct the correspondence? For example, you say that, so let me put, yes, I think this is what I want to do. So you say that V1 is, I will put an equal, but it's the identity. And then you say V2 is the first of the matrices, and then all the way to Vi being G1 times Gi minus 1. So you see that this condition here says that when the nth vector comes back to the first one. Okay? So it's the closing condition. And you work a bit to figure out that this prescribes the length. Okay? This particular description I've taken from a nice paper of Zé Agapito and Leonor Godinho, even though the correspondence, I think, was known before, but they spelled it out nicely, so I cite them. Okay, and this is all I will say about this relation, not because it's over there, but because I don't know more about it. But it's a really nice, I mean, it would be nice to work better on that relation. So if somebody has some interest. And the other relation that I want to talk more about is the relation with the moduli space of parabolic bundles. So, moduli space of parabolic bundles. So for that, I will be more detailed. Let's consider E over P1 to be a holomorphic bundle of rank 2. Of course, you can develop the theory. Yes?
I don't quite understand the correspondences. So on the left-hand side, is it all representations, or just that satisfying some constraint?
On the right-hand side is what?
On the left-hand side,
Yes.
because there should be some.
No, of course, there should be a quotient. Come on, yes. Yes, sorry, the quotient. Yes, thank you very much, Jetro. Of course, yeah. Yeah. Good. Okay.
But it's still local systems on the sphere for SU2, right?
Yes.
This is the identification.
Yes.
Presumably now you're going to do the same in a different language.
Yes, using the parabolic. Yeah. Also, as a side remark, because at the end of the last lecture, I told you that you can do what was called the polygon game for any. So remember, we had this, recall? We had this thing that you could take a G Lie group and consider a product, so OXI coadjoint orbits. Right? And then you could take the product of such coadjoint orbit, take the symplectic quotient by the diagonal action on the product of the coadjoint orbits at the 0 level set, okay? And this would be the moduli space of polygons in the dual of the Lie algebra of the group you chose. Of course, if you do it for SU2, you identify G star with R3, and you recover the polygons in R3 as I did before. Again, I haven't seen it very explicitly, but I mean, I'm pretty sure that here you can just replace this by G, and the correspondence will go the same with this moduli space here, CI. Sorry for the very messy, right? And then if you do it for SU2, you get the polygons in R3, etc. So it would be really interesting to investigate this line. There is a rich literature like Goldman action on the space of representation that maybe it's related to the bending. I mean, there is a nice bit of theory that I never studied, but I think would be, I'm advertising it. Okay. Other comments? Good. So what I did instead was the more explicitly was this relation with the parabolic bundles. So again, here the rank could be higher, but let's fix R2. So a parabolic structure is the following. We fix n distinguished mark points so we fix a divisor, n distinguished mark point in CP1, in the base. And then for the fiber over these mark points, we choose a full flag. So this will be, let me keep my notations, otherwise I will make a mess later. Where is it? Here, and here we go. Yes. So, yes, the indices goes increasing. EXI1 containing EX2, X1, sorry, 2, containing 0. So this is a full flag in the fiber over the mark points. Right? So, as you know by now, I like to draw. Here is a copy of CP1. Here I choose some marked points. Each of them come with the fiber. And for this fiber, what I do is I choose a one-dimensional subspace in it. Okay, it's a copy of C inside C2. This is what is called, so this is maybe worth for me, it's C2, this is C, and this choice is, such choice a quasi-parabolic bundle is an holomorphic bundle with a choice of a full flag as above, with a choice as in star. Okay? Now, a parabolic bundle is the choice of a flag and parabolic weights. So what we do is we choose also weights, maybe I'll do it in white, that are 0, beta 1 xi, smaller or equal than, no, not equal, beta 2 xi, smaller than 1. And with this choice, essentially, so we equip the two-dimensional fiber with weight beta 1 xi, and the one-dimensional fiber, which is a copy of C, with weight beta 2 xi. Okay? The betas are called parabolic weights. So, a parabolic bundle is a quasi-parabolic bundle with the choice of weights. It's for today, but again, let me do an obvious spoiler. This rank 2 amounts from the fact that the structure group of my bundle is SU2. If you want to do the G case, if you want to do SUR, you can replace rank R. And if you want to do, I believe, arbitrary G, you get the structure G. I will refer in the end, not all of this has been done. Part of it is my guessing in the sense, if the word, but the SUR case has been worked out.
And the definition, the flag is always full and the numbers are, the weights are always...
Yes, yes. Okay. So there is a notion of stability for parabolic weights that is given in terms of the parabolic slope. So the parabolic degree of a bundle is the degree of the bundle plus the sum of all the weights, beta 1 xi plus beta 2 xi. Here I have all the weights because my flag is full, but otherwise I would have weights with the multiplicities. And then the parabolic slope of the bundle is the ratio between the parabolic degree of the bundle and its rank. So let me write rank of it. Will be 2 for us, but in general it would be the rank of the bundle. Okay? So the bundle E is stable. If and only if the slope of E is bigger than the slope of any parabolic line sum bundle. And it's said to be semi-stable if the equality can hold. Okay?
How are you using the one-dimensional subspaces? Do you require that in the
I mean, I use them to say what is a parabolic line subbundle. I mean, I've been a bit sloppy here, but what is a parabolic line subbundle? Well, if you take L over P1, or CP1, at the marked points, you have your Lxi, which is just a copy of C. So there's, I mean, to define a parabolic structure, you can't do much on it because it's the fiber. And then you assign weight, either beta 1 xi or beta 2 xi, depending. This is if the fiber is the one-dimensional subspace. So the beta 1 was the one associated to the big. So this is when this intersection is just 0. And the other is if the intersection is the one-dimensional fiber. Okay, and then you work out. Good. So with this notion of stability, it's a classical theory now to study the moduli space of stable or semi-stable parabolic bundles. So with this notion of stability, one can define what I call M beta, that is the moduli space of eventually semi-stable parabolic bundles on P1 of fixed rank R and degree D. So let me maybe put a R and D here below. And what I will do now, I will restrict so I will consider the case, let me consider the case M2 0 beta, but the notation is a bit misleading because I want the above with rank 2 and degree 0, and I want the bundle also to be holomorphically trivial. Okay, I make a further restriction. So the result, I mean, this is a consequence of the theorem with Leonor Godinho that I want to present in a moment, but at the level of parabolic bundles, it was already known. I think it goes back to a very nice paper of Lisa Jeffrey, and then you can recover it also as a consequence of our work with Godinho. And it's the following. So for generic alpha, M alpha is diffeomorphic to M, this curly M 2, 0 beta, whenever we have to give some relation, and the relation is the following: whenever when I have a feeling this is misspelled, alpha I is equal to the difference of the parabolic weights at the point xi. Yes?
I'm confused. How does this not follow from the previous theorem? Don't you always have
frame bundles being the same thing as local system, being the same thing as Higgs bundles, and you've already told me that local systems were the same thing.
Yes, it does. You're right, but for the representation or local frames, I didn't give you any evidence. Well, some, but I just thought, oh, it is this, and I will not go into details.
So this one you
but
have
it is, I mean,
more control over what is that actual
yeah, I feel I have more control, but you're absolutely right. We are giving 3 descriptions of the same space, and one, I mean, if you have one of the two, the other follow,
so
yeah.
Let me reframe the question.
Yes.
So you said that you didn't know if that was a symplectomorphism.
Yes.
But all of these spaces are hyperkähler. So
No, I am still at the Kähler level.
The Higgs ones are.
Yeah, the Higgs ones are hyperkähler, but then,
So there is no fit here.
yeah.
Sorry?
This is SU2, is not,
I understand
yeah.
I understand if I complexify it. Oh, I see. So
Yeah.
So you're not picking a particular symplectic structure inside local systems.
I'm not. But I believe there is, I don't know, a classical one. Yeah. So, and the idea of the proof is exactly lying in the blackboard, because what do I have to do if I take, so the idea of the proof is very constructive. We have a polygon M alpha. Let's say now I think of it as a class of maps Q1 through Qn. And I need to give you an element in this M0 beta, no, M0 beta. And this is what? This is just, I mean, the bundle, as a bundle, nothing can happen because I require that is holomorphically trivial. So this is the bundle. All I have to do is give a parabolic structure, but this is exactly what the QI does, because the QI defines, so I need to give you a flag for every of the mark points, but this is saying one and EXI2. But the way to embed a copy of C in a copy of in C2 is exactly prescribed by the QI map. Right? This is what QI does, put C inside C2. And the weights you chose at the beginning when you define the space. So the correspondence is very explicit. Yeah. Okay. So if you have no questions, let's follow Raimundo's implicit suggestion and move to the hyperkähler world. Okay? So let's consider the hyperkähler analog of the polygon spaces. This can be defined, this is why I tried to save this bit of the blackboard. This can be defined just from the quiver by reversing all arrows and doing what is prescribed by Nakajima recipe. So if you reverse all the arrows and you maintain the same choice of the dimensional vector, what changes in the representation of, I will put an orange twiggle here to say that I've reversed all the arrows. Well, what I do is I now gain maps for the arrows going back. So this is plus the sum 1 through n of homomorphisms from C2 to C. And this, I call them just maps PI from C2 to C. And then the group stays the same. Well, we take the complexification, but we have an action of K on the representation of this quiver Q tilde, which is nothing but the cotangent bundle to C2n, right, which has a classical hyperkähler structure. And the action of K on this cotangent bundle is what's called hyper-Hamiltonian, which means that it's Hamiltonian with respect to each of the Hamiltonian structure on the space of representations. And then one can consider the hyperkähler reduction by K at 0 alpha 0 0 levels. And this is what's called the hyperpolygon space. Well, maybe I want to keep this space. This is the hyperpolygon space. So, I mean, what does this mean? What have I done? Essentially, having an hyperkähler action means that you can rearrange, it means that we have a real and a complex moment map that goes, the first one from the cotangent to C to N to the Lie algebra of the group, and the other will go to the Lie algebra of the complexification, and these are moment maps with respect to the real symplectic form and the holomorphic symplectic form on there. The moment map can be written explicitly, and usually when I talk of this on slides, I have them on a slide, but I mean, it can be computed, it's easy to see, but I want to write essentially just one of these components that will be, so if we take coordinate Q1 through Qn, P1 through Pn, and send it to the sum of the Pi, Qi traceless part, and this sum from 1 to n. So this is the first of the complex moment map, the first condition. The other, they can be made explicit, but take a bit of time. And so what we are doing here, we are choosing, this is the intersection, topologically, it's just the intersection of the 0 alpha level set with respect to the first one and quotient by K. And so we are requiring that this condition is 0. It will be helpful in a moment. So this hyperpolygon space, so when X alpha is smooth, if and only if epsilon I of alpha is different from 0 for every I in 1 through n. So you see we are losing a bit the nice interpretation in R3, but the smoothness condition stays exactly the same. This is the one I had defined on Monday. It's the sum of the alpha I for I index at I minus the sum of the remaining one. Okay, this is the epsilon I. And when it is smooth, X alpha is an hyperkähler manifold, non-compact, unfortunately, is an hyperkähler manifold that contains M alpha as the set of, so M alpha sits inside X alpha, of course, as the set of Qi 0 when the alpha coordinates, the p coordinates are 0. The space was defined by Conno. This definition is due to Conno, who showed that they are equipped with an hyperkähler structure. And Philip Bolch noticed that, in fact, you can recover X alpha is as a moduli space itself. So it's the moduli space of polygons for G equal to GL2C. Okay? So in a way, they are polygons as well. You can take a product of, I have raised already, a product of coadjoint orbits for the group, and perform the reduction. You obtain the holomorphism. You perform the symplectic reduction, and you obtain the holomorphic symplectic structure on X alpha. So they are polygons too.
Is it known if the singular case, the singular is subcanonical? So this
I don't know. I haven't seen it. I mean, but, yeah. No, it's not the cotangent space to M alpha. No, it contains it, but it's not the cotangent space to M alpha. Okay. So to continue the parallelism, what I want to say is that now hyperpolygons, so polygon spaces were the same as moduli spaces of parabolic bundles. And the next claim will be that if you move to the hyperkähler structures in terms of parabolic bundles, this amounts to the choice of an X field. So for that, let me define what are parabolic X bundles. So let E be a parabolic bundle as before on P1 with all the conditions I choose. Let me directly restrict to my situation. Then an X field on E is an element phi in the H0 P1, then the sheaf of strongly parabolic endomorphisms of phi twisted by the canonical bundle on P1 twisted by D. I should say a few things here. What is a strongly parabolic endomorphism? Where if I have F from E to E, this is strongly parabolic. If and only if F of E xi sits inside the next one, E xi plus 1, maybe I'm confusing that a bit. Sorry. Anyway, as you see, let me check it and. Anyway, what is the X field? It's, you can think of it, actually I do think of it, as a 2x2 matrix of meromorphic 1 forms, endomorphism valued meromorphic 1 forms. Okay? Yes?
it's an endomorphism of the bundle, so the fibers goes with the fibers. So maybe it's I1 goes with I.
Yeah, I'm off here. I'm sorry. I had a little blank of the. This is not. I do have a strong feeling. Sorry, it was. This is beta here. Where do I have? Yeah. I'm sorry. This was bad. I overlooked at it, and now I have a little blank. What do I require? I want the. Yeah. Well. Yes.
So it will go maybe from xi k to xi k plus 1. So
Yeah. Well, check it in our nice paper. No, it's fixed details. Sorry. Anyway, so the notion of stability extends. So if E phi is a parabolic X bundle, so a parabolic bundle equipped with an X field, whatever it is, very beautiful definition, sorry for that. If the parabolic X fields, then there is a notion of stability. So a parabolic X bundle, if phi is stable or semi-stable, if the notion of stability given before extends to parabolic line subbundles that are fixed, sorry, that are preserved by the Higgs field. And here, let me not define because I will fall in the same. I mean, the notion is that L should be prescribed by the Higgs field, so we should have that. Okay. What matters is that one can define the moduli space of rank R, degree D. I'll put a beta here, and here maybe I put a 0 lambda because I want this to be the moduli space of parabolic X bundles over P1 that are rank R, degree D, and plus the two labels at the top. It means that we want to have a fixed determinant for the X field, and I want them to be traceless. I haven't defined what these two conditions are, so just let them be there. But in a way, they cut out this moduli space in my mind as a moment map does. Okay, so the claim, the theorem that I wanted to present is the following, is the generalization of the one before. So let alpha be generic, and let betas, the parabolic weight, be such that alpha I is equal to beta 2 xi minus beta 1 xi. Then we have that the hyperpolygon space X alpha is symplectomorphic to the moduli space of parabolic X bundles over P1 that are beta stable, holomorphically trivial, so it's more than degree 0, and then all the conditions I have to put there, so plus fixed determinant and trace-free X field. Okay. So, how does the how does the idea of the proof goes? It is, in fact, a generalization of what I said before. So X alpha, I should give a name to this moduli space. I will call it H beta, the moduli space of such parabolic X bundles. And to give such a description, I need to take an hyperpolygon PQ and send it to a parabolic X bundle. So the bundle, again, with this requirement, I have no choice left. It's just CP1 times C2. Okay? The parabolic structure we have seen before how to construct, and it generalizes because we want to find a parabolic structure in the fiber of each of the marked points. So EXI1 containing EXI2 containing 0. But as before, this inclusion is precisely what the map QI does. So nothing is changed. What we are left is we need to construct an X field phi on such. And how do we do it? So what I was saying here is think of this as a matrix of 2 by 2 meromorphic one forms. And remember that the only moment map condition that I've written down is this one. Okay? So if you set the residues of the X field you want to construct at the point xi to be pi, qi traceless part, to be this 2 by 2 matrix, then because you work on P1, you can use a residue theorem for one form, or a version of it, residue theorem, to claim that there exists, and it's in fact unique, one X field, phi, saying that the residues, prescribing the residues of each of the marked points. You use the moment map condition that imposed that the sum of the residues is 0. Prescribed by the moment map condition because of moment map condition. Okay. So as you see, the construction is fairly, the proof is fairly constructive, is explicit. And one reason why we were very happy where we found it is because with, oh, sorry, I should have here put credits. So with Leonore, we first proved that this is a diffeomorphism. And then with Florentino, Biswas, Florentino, and Godinho, we subsequently proved that this is in fact a symplectomorphism with respect to the holomorphic symplectic structure. Okay. So. I'm not, yeah, I don't know. Yeah. But you see, this is in fact yeah, one should see what is the symplectic structure that you define on the modular space of parabolic bundles. I mean, in a way, the construction defines one symplectic structure there. But, okay. So, as I was saying, at some point we were wondering about, where did I put the eraser here? About the wall crossing for hyperpolygons. So how does the structure of the hyperpolygon change when you cross a wall? In fact, thanks to this isomorphism that we proved, we could realize that it does not change in a way. So the description I will give is a kind of translation from Thaddeus' work, Variations of, on modular spaces of parabolic Higgs bundles. So he worked out in detail the wall crossing for parabolic Higgs bundles when beta crosses a wall. And then we essentially translated his work back to the hyperpolygon case, adapting, I mean, it does it in bigger generality. We computed it in our case. So what happens is that there are some relevant submanifold that can be defined, for example, using an S1 action on X alpha by multiplication of the P coordinates. So this S1 action, we take a lambda in S1, an hyperpolygon PQ, and we say that the action is just multiplying the P coordinate. Okay? If you think of it in terms of the Higgs field, because of how it is our construction, multiplying by an element in S1, the P coordinate, just amounts to multiplying the Higgs field by the element in S1. Okay? So in terms of the Higgs field, if you want to make here a parallel with the S1 action on H beta, this is just multiplying the Higgs field, E lambda phi. You can see it easily. So this S1 action is Hamiltonian, and there's a moment map that is, of course, just so at PQ is just half the sum of the norms of the PI's coordinate squared. This is very classical. And the fixed points for this S1 action are described by what's called XS, which is the collection of those PQ in X alpha, such that we have two conditions. So essentially, we have a partition in the index set 1 through n, and we have that some of the QI are all positive proportional, and the others are all positive proportional. So such that S and S complement are straight. And the Pj are 0 for every j in S complement. So what does it mean to be straight? So S, an index set in 1 through n, is straight if and only if the Qi coordinate is positive multiple of any other in the same set. lambda j positive for all I and j in S. Okay? If you think in terms of polygons, this means that the vectors vi corresponding to the indices in S are all aligned. We have seen it on the lecture on Monday. Of course, this will never be possible on the polygon sets. You can put, I mean, not in the, only in the critical situation. But in the hyperpolygons, you have more generality. And so these components are, the components of the fixed point set are these xs, and you have one for each index set S that is a short and of cardinality at least 2. Remember, short means that the epsilon S of alpha is negative. That's scalar quantity. Okay? There are indices. So you have a bunch of these critical components, and you can consider their flow down to the minimum following the gradient of the Morse-Bot function, the moment map. So these flow downs are what characterize the wall crossing for our hyperpolygons. So so maybe I could mention that these XS are in fact projective space. They are diffeomorphic to projective space of dimension cardinality of S minus n, and this characterization of the fixed point was also due to Kono in the same work where he defines the hyperpolygon spaces. So if you call US the flow down from XS following the gradient of the moment map, then you have that crossing a wall of equation, a wall WS, okay, we had defined it last time. These are the alphas such that epsilon S of alpha is equal to 0. Then we have that crossing such a wall replaces this replacement. There is a Mukai transform that is the blow up of US, and it's the blow down along the cotangent bundle to US complement. But as these things have the same dimension, in a way, you don't see the wall crossing, meaning you don't see it means that the moduli space of hyperpolygons X alpha so let alpha and alpha tilde be generic. They can be in different chambers, doesn't matter. Then X alpha is diffeomorphic to X alpha tilde. The wall crossing I described for polygons the other time. The wall crossing for the polygon spaces M alpha can be realized as, I mean, the relevance of manifold R involves the following. Involves M S alpha, which is the intersection of US with M alpha, and MS complement alpha, which is the intersection of US complement with M alpha. There should be pluses and minuses to be coherent with last lecture. Okay? So at the level of hyperpolygons, there is a Mukai transform that replaces one component of the core or of the nilpotent cone, one of these flow downs from the critical components, by another one. But they are same dimensional. So, I mean, there is not, I can say that, I mean, yeah, you don't see a change in the diffeotype of the manifold, but you recover the wall crossing for polygons by looking at how they intersect the minimum of this flow down, which is attained where the q coordinate are 0, which is the polygon set. Okay? So, yes, I should briefly resume, and I want to resume saying a few things. So, as I said last time, the wall crossing for polygons for the group SUM has been done by Carlos Sotillo and Florentino and Godinho. So, it would be interesting to see what is the behavior for the hyperkähler analog. The hyperpolygons have been generalized in several ways, so that I wish to mention because they are nice works. Where do I erase? Maybe here. So generalizations. So there are nice works that, so what we did was doing all the Kähler and hyperkähler theory for star-shaped quiver, right, with something like this. But of course, this was relative, I told you, to the group GSU2. If you want to replace your group with, for example, G equal to SUR, then you will have to consider coadjoint orbits of SUR that are flags, essentially, in CR. They can be full flags or not. And this will be taken into account by considering this quiver, you know, you have longer legs. How longer? Well, it depends on the coadjoint orbit you chose. So, for example, if in SUR your coadjoint orbit is a full flag, you will have here dimension vector for this. So now I will put the dimensions, okay, here. It's a bit. So this will be dimension R, R minus 1, etc., and all the way to 1 if you choose a full flag. But you can also take a coadjoint orbit that is not a full flag, and maybe here you have R minus 2 and 4 and 1. I mean, you can play around. So you have longer ray. These are all inward pointing, of eventually different dimension you can do. And if you consider, if you do the construction just relative to the group of automorphism so that you obtain from this, you will obtain the moduli spaces of polygons in the Lie algebra of SUR. And the wall crossing was done for the case, so Sotillo, Florentino, Godinho, and Sotillo. Even though I don't think they use the quiver language, but anyway, they did the case for 1R. So still just one leg, but you choose a different dimensional vector. But you can generalize. So this was for the wall crossing, a recent work. I think the first time where I saw this appearing was in the PhD thesis of Jonathan Fisher, who was a student of Lisa Jeffrey. And then he has a nice paper with Steve Ryan where they further a bit the study. And then another generalization kicked in because, I mean, all these things would correspond, I told you, to polygons, to parabolic or parabolic X bundles for the group G over P1. But you may want to generalize the surface, and instead of P1, considering a genus G, Riemann surface. And if you want to put the genus into account, you put G loops in the center. This will change your P1 for genus G surface. And this, learned recently in Romania, was first done, where did I put the reference? Oh, damn, sorry, well, this was first appear in papers of Hauser and collaborators, which, sorry, but I can't find the reference, and then was further studied by Steve Ryan and Laura Shaposnik. The combinatorics gets much heavier. The ideas generalizes, but the combinatorics gets much more complicated. Thank you very much.